in to decide what you should put as what values, because you know that these will actually end up in registers. So you need to know sort of like how many of these are actually going to go into registers and so on for this to even make sense. Because like the idea, I think, like with LLVM was basically, okay, you can just put this on the stack and it will work, right? Because that it worked on X32, and I guess in most places it would work just as is. But once you get into, and you don't need to worry about the registers, how many there are and so on. So it's like a pretty high level. But since you now need to know anyway what the registers are, because you need to place them in, like do some allocation, like okay, this one will go into this. I need to know how many integer registers there are and how much room there are in each of those, like to put these in. And so it gets fairly complex. And I haven't looked at the Win64 ABI. I was told it was much simpler than the X64. But anyway, what it basically amounts to is in my code is sort of encapsulated in this ABI arginfo, and we have these modes of passing things, and these are like actually the way it works in Clang is that you only have like this part, right? So you have the indirect, you have the expand, and so on. But I added more types so that I more sort of could have more specialized information, so I didn't need to like figure it out later on, because that was really hard to read the code and everything. And then I decided, okay, so it's not that complicated. I can make this code simpler or something like that. And what I'm looking at now, like this is it's weird, right? Anyway, so here in this code, this is like, by the way, the only one I've found so far that does this. So here we take something which is like the whatever we figure out that the type is. So we're going to do like some type lowering and see, okay, it's not an ABI type. Then we do like this and blah blah blah, and we can put it on the stack, right? Or put it on the stack, or put it as a register, whatever. So it's like now we have something. If there are no more feed regs, then this we will put it on the stack. Okay. So the thing is, now we want to put this, whatever it is, this is some sort of aggregate. So an aggregate in our cases should be like anything. It's like struct, union, subarray, array. The reason for a subarray is, by the way, is like because it's like a struct. Okay, and these and the complex type. And I don't think I don't correctly handle the subarray actually, but I'll get to that later on. It's like super simple. It's just a struct, but it has like a size and a pointer. Okay, so anyway, so in this case, like if it's promotable, it's not enough. A get which can send it just by putting it on the stack. No, this is just like put it directly like as a parameter. So don't do anything fancy. In this case, we're gonna put, let's do it normally, but we're just gonna put this extend, like say it's like sign extend this or whatever, because it's a small int. So you need to, like if it's a short and you return a short or something, we pass in a short, then you might like say, okay, because you might not be able to put this on the stack, like maybe the stack's aligned, so you have like a four byte slots. So you need to know, like, okay, well, I put in short in here, so it's just going to take 2 of these bytes, and what do we want to fill the rest with? So if you do the int extend, you say like, okay, maybe it's a sign integer, then you want to fill the rest, do a sign extension, and fill the rest with ones if it's a negative number. So I guess this, like we have this, and I don't, the thing is that I don't think we really need to do particular sign extend because it's going to strip those in a way. But this is the way it works in Clang. I'm just going to follow it mostly, but I have this one, and this is something I can maybe just put in direct and put it as an a flag, but I don't do that yet. We go to this one, which is confusing me because here we say like, okay, basically the size might be less than 8, right? And we want to put this. And then we do a queries. And the normal way to do a queries is just basically, okay, we have this, something is like 16 bytes large. And then we take this one and convert it into make it take a pointer to that one. And like we want to, like sort of bit cost this point. We cost the pointer to something else. Like let's pretend this is just no, sorry, maybe it's like eight bytes, right? So we can pretend it's a long. So and then we like just cast to a long, and then we this is a long, and then we pass it as a parameter, it's a long parameter, and then we go back. Oh, I got a long. I just put this in a memory location, do a bit cast, and pretend it's the struct again. So it's the same data. But that's the way you do it in LVM, because you can't do a bit cast on a value. You can take a value and like, okay, let's pretend it's something else. That doesn't work, unfortunately. But it does not so complicated. But what about this stuff? Like, okay, we do that, but the rest of the thing here is, if we take something, an address to something, and then we just, okay, let's get these 8 bytes, but I only filled up 2 bytes. And I think this doesn't make sense to me. So I need to figure out why this happened, and if it actually happens, or if it's just some weird stuff. And the way I figure that out is I go to, I have to do vault, and so to see if I can provoke God vault into giving me a particular result. And let's see, I'm just not going to show you this because I feel like switching between windows on Twitch Studio anyway, like unless you have the turn off, like follow the pointer, like the mouse pointer, it's sort of a mess. So anyway, I'm now, I have something which is that was too big. Okay, I have something else. Let's see. I'm going to remove a bunch of stuff. Okay, now I have a fairly small one. Okay, so this one is what? It's 60. It gets turned into a 64-bit value. Let's see what happens. So, okay, it's a 64-bit value, but it's aligned to that, I guess. Let's make it even smaller. So now it's definitely a short. Okay, so I'm looking at the God vault. Sorry, I can't show you this. It's okay. Let's see. Okay, and now it's an in 24. Curse you. Okay. Sorry. I'm just going to put some stuff in here. So int a. Sorry, you're not going to see this. Double A, double B. Just going to see when it gets turned into something else. So, okay, that didn't work. Oh, need to. Oh, damn it. Okay, I'm. So, trying to figure out what happens. So I need to use. maybe a long struct. So okay, I'm sorry you can't see this, or maybe I should just let you see this. Okay, that was still adding more stuff. Long C, T, long E, F. How many registers are there? I'm getting the same. Oh, it's weird. I'm still not hitting that particular problem I wanted. So if I do something that has like a lot of parameters, I still get an I-24 at the end. So this doesn't happen. So, oh, it's a result. I think this might be returned. Let's see how I get this. Okay, we're going to classify this as memory. Oh, hang on. It's when do I get it as memory? So let's see how it can end up as memory for sure. So we classify this one. I want some way to sort of figure out that this is actually memory. Oh yeah, maybe I can do this packed. So attribute packed. Let's see if this worked. Alright, now I have a packed thing. Still get the I-24. This is bad, so I have no idea how to get something put in memory. So a member might not be aligned. With whatever offset there is. So but what about this? I mean, a struct that is larger. Oh, if it's larger, then it ends up in memory, and that doesn't happen. So, like looking at this, how do I actually put something, like force something to go into memory? Yeah. Maybe if I have something, I don't know, I won't have any high class. I wonder if this even happens. So this is the problem, like when you look through Clang, because there are things that are supposed to maybe happen, but I don't even know if they happen. So yeah. But it's still sort of weird because it gives you like an I-24. And I was like not quite prepared to get an I-24. I'm not sure that I get an I-24 if I run my code. I think I'm going to fail on somewhere, like fail somewhere. It's sort of really weird that I get that. Like I can't figure out how this code would actually make it go into memory. Like so, size is bigger than 16. But how can that happen? Oh, it's a 64 byte. Sorry, I am idiot. Anyway, so here if it's big enough, right? So then you can't pass it. Okay, obviously, unless because if it's in memory and the types of blah blah blah, and the size is bigger and the type size is not, or is not in union, and the size is not the same, like it is not the only thing, then we'll fall back in memory. But since this one is pretty big, it's going to be like 16, so it's not going to give you an example where you have like less than 8. So here we won't get the memory here. And here, if the type ABI alignment, and if the alignment and the offset, like sort of, if the offset, but the offset is like always going to be like 8, I think, like 0 or 8. So let me just check this, but I am pretty sure that the offset will always be that. Let's see here. So the offset base might be low or high. The class, so it's going to be low. It's going to be low. And here is, let me see. So the offset is something. Let's classify the argument type. We do it with 0, and then we do the classify again, quite possibly. So here we got something else, but that's inside of the struct union parts. And we only have this one, and it's starting at 0. And this is classifying like this. So you classify with 0. How do I get even the high class here? I don't need to. There must be something wrong with the whatever I'm using here. So find usages of classify. I'm pretty sure that it's not just that one. So here's something. Yeah. In this case, we get the offset by taking the offset base plus the member offset. Now, the member offset is, I don't know if this is right or not. So, okay, it's not aligned. New offset afterwards is not aligned. Then we go into memory. And we do a classify, and we default to memory. So, I mean, I guess this would give you a memory version. So you get this one, it's in memory. So the argument is in memory. We put here, get an indirect result. And then we should go here. But it doesn't. I think, I mean, I have to look at a bit at Xcode. So I can identify where that happens. So I have already looked at this. So on stack, let's see here. So where is that code? So if it's a non-stack, then get natural align, blah. Then if the alignment is 0, 8 and the size is less, then get some, oh no. It's going to get the type and it's going to like pass it as an int, but the size that it actually has. So it's a API direct queries, but it's going to like a type that I don't even have. So like a direct queries, but it's like I don't have that type because it's smaller. So in the case, let's see how I use this direct queries thing. So let's say that in case the direct queries is like emit convert, hang on, so it's the queries thing. I would need to have something that is a type which is like a fake type here. So I'm just going to create a type, I guess. Do I have access to LLVM at this point? Yeah, I do. I need to so the direct queries thing, let's see what it can be. So let's see, I can either I am going to create this one with the result type, whatever that can be. It can be some like a vector or something, whatever, really. So I wonder, I'm just going to make like I'm going to add something like a, this is direct extend, so I'm going to like API org direct queries in bit size. So like this. And that one is going to have its own struct, so it's going to be like struct. And it's just going to contain the byte size. Let's state that. So byte sized. We're just going to call some direct int queries int size. So when you create one of those, then you have a special function for that. So it's going to be new, and we're just going to say it's going to be like unsigned byte size, and the byte size has to be assert a byte size is bigger than 0, and it's going to be a direct queries int byte sized and let's say direct it's int sized in info direct int sized by size. Okay, and it's going to be like by size. Okay, so there we have our new function, and that one is going to give us the weird thing with like not completely not not real types. So it's going to be like direct queries, incised, and the size of this type. So this is what we're going to return here. And now we actually done that. So that's good. Indirectly aligned. So this one has a special, this one is the indirect, and we add a real line. We don't do that on the other. So okay, whatever that is. Okay, so now when I push this button, it's going to complain and say like, okay, we have a lot of places where we didn't do anything about this particular thing. And here we have a function type. So what is the type for the return argument? And we don't have a return argument that is that one yet, but we're just going to do that. So ABI direct queries is size, then we have a return type, which is type is LVM. No, we're just going to create a new one. So in type in context, we get the context from LVM, and we say, okay, number of bits. So it's the thing we stored, incised, byte size, and times 8. Right. So and then we just break. So we have that case fixed. And then we have is it indirect? No, it's not indirect. This is still direct. So a direct is actually like a parameter. So indirect means that you give the pointer instead. So anything normal will be direct. Okay. Emit parameters. Now we got this from like a parameter, and now we have to do some stuff and do a queries, and we have those here. So this is the variant of this one. So then you like have you want to like direct queries inside. So you take the parameter. Now that one will be that particular size, and now we have this function, which is it expects the type to be a type and not a LVM type. So we have to change that to be a LVM type, backend type, so like that. And now we can have let's call it queries. Maybe that was better. So let's see. We're just going to get a lot of errors now, and it will like break the. Then we have this one. That one type of query. So okay, and I have to get back to the original one. So it's 2 queries. So that would be an LVM type ref. And I guess we skip this. We can do that. We can do a LVM get ABI type is, what's this? No, LVM ABI size of type. So this type needs to be the same as the original type, and we need to get the data ref. So maybe I get this a lot, so maybe I need to be a convenience function for this. I should do that now. So we have LV something like unsigned LVM API size. So that takes a LVM type ref, and then it's going to give me a, do this, just return LVM ABI size of type, and then we need to get the target, so that one is global here, target layout and the type. Okay, and this is going to give me the type in bytes. That's good. And then we need like store size. I guess we can take that one as well. So like the store size of type, because sometimes you want to check that. Just to make sure that everything is agreeing. Okay, so this queries type isn't needed anymore. I'll take this queries version, and we have the queries like this. All right, and then we have the other one. So this is not a pointer. And let's take this, and we are emitting an alloca, but thing is we want to emit. Okay, so we're going to LVM. Oh, this is bad. So alloca. Okay, so this one we want to use the raw one, and it's going to use the alignment that is, I guess, default for this one. I was going to check what Codebolt does. So when it puts something in there, I need to remove the crap here, since I added a lot of things to test this. So let's see here. Taking that I-24 is going to do a Zext. Oh, that one. Okay. And then it's, hang on, is this optimized or something? Because that would not be good. So let's see if I had some optimization running. Oh, it's so on. Oh, banned, damn it. So I need to look at the original. So okay, so it gets the I-24 and it's going to align at the 4. Okay, so it's probably the alignment. So we just going to get the LVM might be, yeah, let's add the alignment as well. So ABI alignment of type, or maybe yeah, I guess so. Okay. Maybe I shouldn't use the ABI alignment, I don't know, but let's do that. So ABI alignment of this type, right? And now this is going to emit the alloca. Oh, and the store, hang on, it's just going to do a load here. And the load should be aligned as well. So maybe the load will be automatically aligned to yeah, I have to think about that a bit. Loads here are not aligned, but okay, anyway. So now we have this one. I need to do a VM type for that one. Oh, okay, so this is the inside, so hang on. So we're going to create that type, whatever that is. So it's an LVM, type in context, and then we have the context, actual context, which is a bit confusing maybe. And then we have the info containing this thing, and we take those as bytes. Let's see here. So we get the in type, queries incised byte size. Okay, so now that's a bit junky, so we have to make the value into a convert value. So I guess like this, LVM value ref queries value, and that one is, hang on, there it is. So value, and then we have like the type, and let's pull that one out. So LVM type queries type. Okay, so I prefer to have stuff easily readable here, fairly easily readable. Not put everything in the single line here. So at least for I think for C that makes a big difference. Value queries. So it's super nice. Okay, queries, and I need to make sure that it's okay. That looks okay. That looks okay. But maybe it's not quite done yet. So let's see where everything needs to be fixed. So okay, we have this case. We have the queries type, and here we have something else. So in the incised version, we have similar to the one before, but now he's just going to generate this this in type in context, number of bits, and it's again the info and the sorry, this one and times 8. Okay, we're done. Okay, oh, params. Yeah. Oh, and let's see where it breaks next. So here we are in the return value. So, oh, the return value, obviously I didn't want this. Type, I need to get the actual type there. All right, we have also the one we did just before now. It's going to be the same thing. So queries inside. So we're going to go forward, and this is for the return value, right? Okay, so hang on. So this is different. This is when you emit a return value. So if you are queries, then you do that. If not, then you do again context emit return value, and you do a context, and you do this conversion. But it's going to look different. So now LVM value I sort of hate this, that you have to do these, that you don't have these implicit. It goes away with in C3, but we have it here. So this is like a sort of a wart on C. So the type is this, whatever, and maybe like in if we had some nice encapsulation, I could do this as a macro. So you could this or function, but it feels like it's not going to happen so often, and it's nice to be like really explicit. So everyone will see what happens here. So you don't need to jump through all of these steps to find out what actually happens. There is fairly straightforward, just some calls here compared to Clang. Okay, so here we get the here's the return type, we're going to emit, no, we're going to set the return type, add attributes, yeah. So we don't need any attributes on the direct in this case. So we don't put anything there. So there are three like different places where you add information because you want to set like attributes on things as well. So here is where I pick up the return value. Like there are two places. Like first, I might need to do a return parameter in case it's indirect, but that doesn't happen here, so that shouldn't be there. Now we have the indirect read-line, blah blah blah. We have the int extend, and we have the direct queries, and then we have our like this case with. We already did this actually, so I'll see if I can copy paste this from. No. Oh wait. Well, I'll do it twice. It's so easy. So maybe I don't know. Maybe I could just take this and do it differently. I don't know. Okay, so we have this same thing, but we just do it with something else. So I need this temporary LVM type ref. So the type is LVM int blah 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 context. Now we have done this a few times already. There should be we should have done a method for this. All right. Oops. So the context is there. This is the byte size. Now we have the type. So then we have type, and then we do the queries with that particular type. And then we add that as a vector, and then we do a break. So, and then we have next time we have queries. We just, this is, so this is when you get the return value back. And then we want to convert that from queries, and then we want to do again the in thing. So LVM, I'm just going to copy paste that. There we go. So then the type is I usually will go back and clean this up later on. For now it's this queries insights, so there we go. Ooh. All right, let's see if I do one of those things with a small one here. So this is just a very small, and I don't need any line on this, and maybe I have a char. What did I remove? Oh, so I need this one, and I need a char here, and then you should get the weirdness, and it might hit some other stuff as well. Boom. Type inside by bit size illegal bit size 24. So good. We hit some thing here. Type unsigned by bit size. I understand that this breaks because I don't have any like this bit size where it has this 24-bit. Okay, we're just going to trace it from here. boom, and then we get gexint at offset, and then we get like, okay, we want a, all right, here we go. Now we are, this is good. So let's see, we get this thing here, which is not like fully sized. And we end up like going in here, and if it's an integer, is the promotable integer, but this is not going to be like a this is not going to work, right? Why is it giving me a that sort of weird sized thing? So maybe it means that I am doing it wrong. I should, introduce these fake sort of types that have an offset which is, where we have like these 24 bits. That would certainly make this work. I'm not 100% sure that this is a good idea. But I'll just need to take a short break. I'll be back. I'll get some tea, and I'll get into that later on. Bye-bye. Okay, I'm back. Are there any questions? Right now, no. So I've been thinking a bit about this. None of the solutions are any good, because if I introduce like a fake bit thing here, then everything will start crashing down. And I think if I understand things correctly, what it actually says is basically, so it relies on being able to it still has like the correct alignment, so it will actually be a for example a 32-bit thing that is passed on the stack anyway, which is I think anyway. I'm just going to check that. So if I have for example, I put this one which is small, it's still let's see if I get the right code here. So I have this one, okay, the foof, and then I have the check. So it's a 24-bit value, and then the question is what happens if I put a small byte afterwards. Byte bxa afterwards. And what happens is that you get a I-24, and the resulting code is where is it on the stack? That's the question. So if I get this one, where is it from the stack? So int a equals a, int b equals a plus 1. So that will be, let's store it. So here it is. That is loading stuff from this one. So it's 12. It takes the stack and it actually I need to have something with larger alignment. So it's, there it is in 16. And there it is in where? 13. So it checks, actually it uses that one. That sucks. So what I was checking was, okay, maybe it doesn't really use 24 bits. Maybe it's just using 32 bits anyway. But it is actually using 12 bits. So that is bad. So when I get this in type at offset, what do we do? It's like the result type, and then we take this result type and then we put that in a return or something like that. So that's what it could be, high or low. And here's the direct queries. To actually inspect this Yeah, it's an integer. I need to look at that. It's promotable, and I would need to, use the LVM stuff all the time. And the reason I don't want to use LVM at this point is because I want this to be still in the sort of a middle end, and so I don't want to touch. I don't want to touch things. So maybe I need to do a create a type, special type kind, which should never go into the front end, and it's like a variable like this type variable int back int. So that is bad because there is so much in here that relies on ordering and making sure that okay, this is an integer and so on. So I'm not super happy about that idea. I could make it a 32-bit integer, but I would make assumptions. So I mean, it's sort of a struct, right? So it's sort of a struct that is takes a this int, and this is bad. Or actually, I mean, the bad thing is that it actually passes this up and uses it as this type further on. So at least I know this result type can mess up things. So now I have to, I guess what I can do is to sort of clean up everything here and see if I find some, maybe there is some workaround. Just thinking if there is some way to do this. Because it has all these funky stuff and I don't know, it's like passing this up, I could make a union. I can make a union so that basically says, okay, this is either a type or this weird half type. That is a possibility, and that I would be able to detect when I have to do it differently. I don't know if that would work. So like here I have this weird type, so and then I take this weird type, possibly weird type, and then I use it as a result type in here, and in this case it's like an integer. Is it promotable? I don't use that really, and then so the result here I put it in a pair return. Let's see what I get, where I get it elsewhere. So it's in the return. Get the type at offset, and there are two places, but that's the return. So maybe that would be possible. So let's introduce for the x64, but it's probably going to be needed elsewhere. So I need to go to the ABI info definition, and now we're going to introduce a type def struct ABI type, and that is either going to be it's going to be a type, or it's going to be, we have to introduce an enum here as well. ABI type kind, and it's going to be like a ABI type plain, ABI type int bits. Those are the ones we know about to begin with. All right, maybe we can just call this one like this, so it gets, this will make this more correct actually, but it doesn't look as nice. Okay, right. So the ABI type, we have either we have an ABI type kind, which is kind, and it just needs like 2 bits right now. And we have a union, of course, that's why we have a kind. So we have a type, or we have an unsigned bit int bits. Okay. Right, and then we know that this one will return ours as a ABI type instead. So we're just going to return, we need a function to get us, like, we can do it like this right now. So ABI type oh right, we need a helper for this. Let's see if there's, like, where did the pet put all those helpers for creating. These are APIs. So let's see. We have this find usages. Oh, there it is. So oh well. Okay. So API type API type new plain, and just going to take a type. Type and go. Okay, so and then we're going to take actually there are other ways to do this to if you want, we wanted to save memory, but let me just do this like this. So right now memory for this is not a super high concern. We are not going to create a lot of these new int bits. Unsigned bits, int bits, ABI int bits as bits, and we need, of course, to put the type there. So type is type. Okay, we need to put these in the header. New int bits. Right? Okay, so we can now express this. I don't know if we need to actually allocate this. This is so small, right? So we could actually put that on the stack, but right, maybe we want to do this. Okay, well, let's do it like this. It's right for now. It's just an experiment, right? So this should be fine. So it doesn't contain any user data again. It's just this type, right? And here we get this, which will pass on whatever that is. So here we just pass on whatever that is, and here we get the new one. So type, ABI type, new bits, and then we have this, right? So here we have something, it's a long, right? So we can just return a well, we can just return the long, right? There is no need to do anything fancy here. So we already have a type. Let's do that. Okay, so now we know that it will return this one and things will start protesting. So here, with an expression signature ABI. Oh, it's because of this name change. Name. Like this doesn't make sense. Why should this break? Okay. Okay, so result type here is actually not a type, it's an ABI type. Now, and type is integer, that ABI type is integer. ABI type, we have this function then. ABI type is integer. And ABI type. So if return ABI type kind is this one, or the type is integer of the embedded type. So and expose that one here, I think. Okay, so we have the ABI type is integer, and then we want to, is it promotable to integer? Then it does that. Isn't a promotable integer, and that is like, is the actual type short or something. So then this as a Z type it offsets. Okay, so this one will also need to return an ABI type. But that one is always going to be a real type, I guess. So why don't we make that simpler? So we actually return a type, but we're just going to wrap it. So get a new plain type, and that is it with that one. So and the high part, which also needs to be like an ABI type then. And new direct high, and the high is going to be, now an ABI type instead, unfortunately. So it's going to be an ABI type. And that would fix those things, and here we go, create ABI type. Alright, and then we have a vector type again. We just do this wrapper, because this is like the only thing that I can't express in my type system. Everything else is possible. And then we have this one, and it will obviously take the two ABI types. So type size for that, we would have to take ABI type size. And also, alright, so this is so messed up, we have to do all these things, try to get like the alignment for that and so on. Alignment, so it will sort of type it. This will not be, so it will be take like the ABI type, ABI alignment, ABI type size. Now we need to redo everything for these. Yeah, I'm happy already about that. Coding internal, those functions, right? ABI type is integer. Okay, so ABI type size, and then we do a switch over type kind. So case ABI type bits. In that case, it's going to return the type bits divided by 8. Case ABI type plain, return the type size of the embedded type, and then unreachable, everything else is unreachable. And then we can do the alignment. So we're going to say for this one, it's going to be like the ABI alignment. Okay, but for this one, you're going to like round up to the closest. So let's take the bits and so nearest power 2, highest power 2 of these bits. Type why is this not max highest power of 2? And then we take type unsigned by bit size. So we take near like this, and then we take the ABI alignment of that one. ABI alignment. This is going to be correct because we can take like the next one, and that is going to be next highest one, and we're going to do the alignment of that one. I think. Yeah, that should make sense. We're not going to do the smaller one, or yeah, I think the alignment was like I have to check. So the alignment of this I-24 as 1, but the alignment of I-24 is 4. So it's actually not going to put any alignment on that one. It's going to treat it as line 24 though, like 04, sorry, 4. That's super weird. I need to check what it does with when it has non-integers, like when it gets the alignment, get ABI type alignment. So it's going to get the alignment of a type if it is so it is a type, it's not one of those normal types, so it's type ID, arbitrary bits. So what they are going to be is we're going to take the integer alignment so whatever the alignment is for an integer. So let's see, so my expectation then is that if the alignment is in this case, then I could like assume that it will be the alignment of whatever an int is, so the C int version. So just going to make sure that that is correct. So I will test that on Godbolt. What happens if I have something that is a bit weirder? So now I have something which is 40. Okay, so I get an alignment of 8. So, and if I have something 8, of course, so 24, I get 4. I am assuming now, maybe incorrectly, that a 24-bit one will get the I have to check this. So get neg-bit line, if it's going to get the float line type. Okay, and I get the float line type, and now I have it's going to get the type align. Okay, then get the alignment of that type. First I get the type, and then we get the type info, get the known min type. So get known min type. So there's a minimum value. So it's see what it says. Okay, I have an integer alignment. So, and I can just go up. I just think that I think it behaves just like the code I wrote there, right? Like this. So it's going to assume the alignment of the next highest power of 2. If it's not like this. So okay, I'm just going to put this in here and just going to printf master. This is weird, but so we'll just make sure that this is doing the correct thing later on. Okay, so we have this function. Not the size, right? Okay. Now I have some helper functions that we will need. Is float. Type is float. Okay. Now we need obviously another function which is type is float. ABI type is float. So ABI type is float. We have this one, so we need a ABI type is float. Right. So this feels like a big hack, but maybe it's necessary. I don't know. Okay, we have this one, and now we know it has to be like this ABI type and this ABI type. So and now this becomes an ABI type. This becomes an ABI type. All right. ABI. Okay, so it's going to do like this. Maybe we have this LLVM type, right? So we're going to extend this to get like a defined type ABI type and context get LLVM type ABI type context type. Now the gen context LLVM get type get LLVM here it is. So now we want this ABI type right. Now we are doing this, we get the ABI. So there are two ways. Like first, if you can switch over here on the type kind, or in the case that this is a regular kind, so it's a type plain. In this case, we're just going to return gen context and the type over type. Otherwise, return LLVM context type in bits, right? So, and this is unreachable. And okay, so that's why it didn't work. LLVM ABI type. Okay, so now we made our ABI type ABI type. Oh, wasn't that it? Type ABI. Okay. That seems a bit inconsistent. So we're just going to change that to this. All right. And now we have this. All right, so the low type may be to be extended into something else. I don't know, ABI type. Anyway, here it is. We have to look at that later on. So maybe the extend type should be an ABI type as well. Then everything will work the same way. I think we're forced to do that. And the low extend is ABI. Okay. If the return type canonical, if the result type kind is type ABI plain, and now we have this return type. Now we can do this. And then we have the new direct queries, and it's going to take the ABI type, of course, instead. This one is going not surprisingly. And this means it's now this. You see how everything just bubbles away around here. It's like ABI type. The thing is, though, we don't need this anymore. So in this case, when we had this insize thing, it's going away. So we're just going to remove this one. So this is the advantage of doing this change, I guess. So instead of getting this one, we are going to be ABI type, queries type. Now that means this goes away. So all the work we did just goes away, but that's fine. Like, this is the way things work. I think the queries, maybe this one, yes, it's okay, it's done. Good, that's good. So we try solution and then it doesn't work, and then we need to do something else, and that's perfectly okay. That should always be like you don't know what's going to the best solution is going to look like, and it's definitely not this current solution, but this is a way we work towards the solution we want later on. So it's super important we don't, think that this is a problem anyway. So ABI type plain. And this might seem a bit, a slow way to do this. Okay, so this is interesting. Here, actually, this is wrong. And the reason for this is that we want to be able to, okay, we could do this, I guess. But we wanted to, like, there is no reason why we should do this. But we can do it anyway. Because in here we always know it's the right size, right? There is no way to get it get an arbitrarily sized one, but we do it anyway, I guess. So here we get another one which looks like that. In this case, let's do it. So keep forgetting. Right? Again, here we get this, and here, in this case, like, I get use direct. So we do a, so maybe we should do the ABI new bits. I mean, it's maybe a bit clear that this is happening. I don't know. I think that maybe it is. Like in these cases, ABI, because we are doing a transform anyway. So maybe it makes sense that we use this functionality. In this case, it's an MMX type. I don't know, like it's an int anyway, so I don't know. Maybe yes, we do it like that again. So it's an long, so it's like 64, sorry. So here we, so it's, yeah, it's a 64-bit, and that way we don't need to use save whether it's signed or unsigned. Okay, so here it's a signed one, and this one is the one we don't use anymore. So in this case, we just create a new direct queries with, maybe we could have used that ABI new bits and the size and times 8, I guess. And we remove this one completely. And we get type here, we don't expect this one, so we need to expect, I think this is on the, oh, here we have another one, we can remove the incised one, types an integer, and ABI types an integer instead. And is type is promotable. Yeah, okay, this is fine because this is not what I'm looking at. So, and again here we have this one, and it's not an ABI type, so I have to wrap this one arg. Let's see here. So ABI type. Create. So maybe this was a mistake here. I just not returning this one as a ABI type. I just felt weird because it's like it's going to return the same things anyway. So let's see if I ever use it. No. Oh, okay. Like make it more consistent. So create ABI type plain. So we do it here instead. ABI type new plain. ABI type new plain. Right. And then we will have to go back and fix that because suddenly, oh, we have the vector on as well. So, and type ABI new type plain. Okay, and then we have the type, and the type might be something. Create ABI plain. So here we have something based on size. Okay, Yeah, well, again. Right. Oh, and let's see here. So API type, we don't need this anymore. 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 And we don't have this anymore, I think. Yeah. So we don't have this anymore. So instead we just have this one. And we don't use this one. Alright, almost done. And let's see what happens. Oh, it compiled. Magic. And we get our I-24. We align that. Yeah, mostly it looks okay, I guess. So it's done. That part is done. So we're getting closer and closer. I can look at the to-dos. I will quit here because I will need to do other stuff. And I need to go to bed soon. We know we have these. I think the HVA is not. It's probably nothing I should be doing. It's just a direct one. So what happens here? And then this is the return API. If you return a direct thing, and then there's the int extend thing, and you don't need to do anything, I guess. So the direct one is simple. So I think in this case, the int extend, the default behavior is fine as well. And then we have like these, which are not done. And this is just, what is this? I think this is a crap from other code that I was looking at. So I just remove that one for now. All right, maybe I should just make a checkpoint here. So getting somewhere with x64. This is just locally. Oh, xc64. Oh yeah. Memories. Okay. Commit that. There are a lot of to-dos to do. Yeah, I know. And I'll look at those later on. But for now, we have gotten, I think most of the way. Maybe not all the way, but we'll look at that later on. It's sort of this code is, I don't know how much code. This is just the x64, right? And just classifying things is 800 lines. It's like taking here's the codegen for the types. This is like 300 lines, and the expression codegen for expressions. Okay, this seems like 2,000 lines, and that's all. Those are all the expressions. And now, this is including the call expression, which is like the main part of it. So this used to be like, let's see, compare with the same repository version. Maybe like we'll compare with history, and it's like when I was doing how many lines for them. It's less, I think. So I'm adding like hundreds of lines of code here. So here it is. The def us here, we have a bunch of it, and then we go through like this, blah 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 blah. But at least it's not like in the client code, which is crazy. But they have the C++ stuff, and they like right now they just put everything in a single file. Like the target has all the targets, and they have a lot of them. So I shouldn't, bitch about that so much. But it's not super readable. Just let's do a few things, cleanups. Slowly getting there anyway. Trying to figure out everything, and maybe this one int extend here could be an attribute that I put on things instead of a separate one, but this is much simpler than the chorus one, and I like having those separate, exactly what we do. Yeah, we'll see. And the indirect and indirect realign just something you can look at anyway. It's not something that's super important to have as a different type, but still, it's sometimes it's nice to know that it's actually doing the realignment, and that you have covered that. So we'll see. And it's interesting, I haven't done the expanded pad yet, and I don't know if I need to. So, all right, thank you for watching. I'll put this on YouTube, I guess, so you can watch later. All right, goodbye.